In the previous video, we talked about partitions in combinatorics, and this is part of the Math Olympiad program and the ISI entrance program of Chinta. If you have not seen the last video, there is a link in the description right now for it. We want to figure out what is SN3 in this particular video. So let me define that one more time so that you are reminded of what we were doing. Suppose there are n numbers in a set and we want to split them into three classes, that is three subsets whose union will be this entire set one more time and whose intersection, that is the pairwise intersection, will be null. So I'll give you an example what I mean by this. Here is an example. Suppose the set is 1, 2, 3, 4, 5. Just 5 numbers are there. So one way to partition this particular set into three classes is like this. You have 1, maybe 2 and 4, maybe 3 and 5. This is one way. What is another way? Well, another way would be maybe 1, 2, 3 is in one class, 4 is in another class, 5 is in another class. So like this, we can count all possible ways of partitioning this particular set containing 5 elements into 3 classes. 5 elements into 3 classes. So this would be the number of ways of doing that will be equal to S53. 5 denotes the number of elements of the actual set and 3 tells us the number of classes we should be partitioning it into. Okay. So what is our goal? Our goal is to find out an expression for SN3. So what is SN3? You have n elements which you want to split, you want to partition into 3 classes. So in the last video we found SN2, a formula for SN2. Many of you responded in the comment. You did a really good work. In this one we will talk about SN3. So let's do that. The strategy would be like this. You take all the n elements into one set and then you take 3 boxes. Let's call it box 1, box 2 and box 3. So take the 3 boxes and what you want to do is you want to send these elements to these boxes and you want to find out all possible ways of doing that. So how do we do that? Okay, let me put this little thing to the right hand side. Maybe make this a little bit smaller. And let's find out the first step of doing this. So the step 1. Step 1 is note that each of these numbers, let's take 1, it has 3 choices for where it can go. 1 can go to 3 different places. Box 1, box 2 or box 3. So 3 choices. For each of these 3 choices, we have 3 choices for 2 where it can go, right? So 3 times 3, total 9 choices now. For each of these 9 choices, for the number 3, we have again 3 choices. So times 3, like this, we keep on doing this. So this is 3 to the power n. This is all possible ways, okay? But we are not done. We have to take into the consideration of the case where box 3 is empty. We don't want any of the boxes to be empty. But it could be so that box 3 is empty. How can that happen? Well, it can happen if everything else goes to the first two boxes. So let's delete all those cases. Let's delete all those cases where everything goes to the first two boxes. So let's do that. Minus everything goes to two of the boxes. Okay, so how does that happen? Okay, maybe everything goes to box 1 and box 2 and box 3 is left empty. That can happen if you count it like this. 1 has two choices, either box 1 or box 2. Similarly, 2 has two choices, 3 has two choices, n has two choices, and so on. So 2 to the power n ways in which box 3 will be left out empty. Similarly, there will be 2 to the power n ways where box 2 is empty and 2 to the power n ways where box 1 is empty. Okay, so 3 times 2 to the power n. This counts all the cases where box 2 is empty or box 1 is empty or box 3 is empty. Alright, great. Now it may so happen that everything goes to one of the three boxes. So maybe everything went to box 1. So box 2 and box 3 are empty. Or everything goes to box 2 where box 1 and box 3 are empty, or everything goes to box 3. We want to avoid those cases as well. So everything goes to exactly one box. We want to avoid this case. We don't want this because after all we want all the three boxes to be non-empty. Otherwise it will not be a partition into three classes, right? Okay, so how does that happen? Well, there are exactly three ways, right? Because everything goes to box 1, everything goes to box 2, or everything goes to box 3. So exactly three ways in which everything goes to exactly one box happens. So these three ways were counted here. So when I computed 3 to the power n, three of those 3 to the power n cases was this case where everything goes to one box. Okay, so we counted it here. Now we double deleted it here. Why is that? Well, when we took the case where everything goes to box 1 or box 2, when we counted this case, one of those cases was everything goes to box 1 and one of those cases was everything goes to box 2. So in one of the 2 to the power n's, these two cases were counted. So in three of the 2 to the power n's, each of these cases were counted twice. So let me write that. We double deleted the cases in the second step. Well, we wanted to delete it one time because we don't want these cases to happen, but we don't want to delete them two times because, well, then we are deleting extra stuff. So we have to add those three cases back. We have to add those three cases back. Now, this particular number, 3 to the power n minus 3 into 2 to the power n plus 3, this number is almost the answer. But you have to take into consideration the situation that we are considering the three boxes to be different. So in our example, 1, 2, 3, 4, 5 is a partition, of course, but 2, 3, 1 and 4, 5 is also a partition. Notice that they are not different partitions. I just wrote this one first here, but that doesn't make it a different partition. So we have to take one more step. We don't want to count these permutations or rearrangement of the classes. So can you tell me the final answer in the comment? And that's just one step away from this particular expression. This problem also does two more things. It tells you something about the principle of inclusion and exclusion in combinatorics. It's a very powerful tool in combinatorics. It also tells you something about partitions. That's the story of this entire video. And it tells you how to count onto functions. So I have not spoken about this yet in this video, but I hope to do that in the next one. It definitely helps us to count onto functions, and we actually found the answer to that question, where if there are n number of elements in domain and 3 elements in codomain, then how many onto functions are possible? So can you answer this question as well in the comment in this video? Notice that we actually already solved this problem. So if you understand the meaning of onto functions, you should be able to answer that just watching this video. Okay, so keep on doing great mathematics. I'll see you in the next one. Till then, bye.